Mercedes-Benz Stadium is not merely a sports venue, it is a globally recognized architecture achievement that integrates cutting-edge engineering and structural precision. The stadium's retractable roof and its symmetric truss system generate substantial vertical and lateral forces that cannot be managed using conventional construction methods alone. To address these complex structural demands, the project employed an integration construction system combining major structure components, the mat foundation, mega columns, standard columns, slab systems, rocker beams, and mega trusses. This presentation will sequentially examine how these structural components were installed and how they interact with each other, and what construction strategies were employed to involve the project's unique engineering challenges. Let's take a look at the foundation construction process of the Mercedes-Benz Stadium. Inside the stadium, the ground is mainly reinforced with geopile and spread soil methods. On the stadium's exterior, drift piles and auger cast pile methods are both used, each applied based on its specific location and role. The stadium's mega columns must support an enormous load of 37,000 kN. For this reason, a simple raft foundation alone is insufficient. To compensate, drill piles are added beneath the mat foundation to transfer the weight to the ground. The process begins by excavating the mat foundation's area to a depth of 3.5 meters, installing temporary structures to support the zone. Next, to support the weights of the mega columns, drill piles with a diameter of 2 meters and a depth of 35 meters are created. To prevent soil collapse during this process, a steel casting is inserted first. After the casting is in place, a rubber cage comprising pile rubber, ties, and cover blocks is lowered vertically by crane. Guide bars ensure the cage's precise positioning and vertical alignment. After placing the rubber cage, concrete is poured into the hole to complete the construction of the drill pile. Once the drill pile work is complete, the main mat foundation construction begins. First, cover blocks are installed at 600 mm intervals to keep the rubber from touching the bottom or sides. Then, bottom rubber with a diameter of 60 mm is placed in a grid pattern at 300 mm intervals, both lengthwise and crosswise. The rubber comes in 12-meter lengths, and where insertions are needed, it is lapped and tied with a 2.5-meter overlap, ensuring smooth load transfer between the bars. At points where the mega columns loads are directly transmitted, the rubber grid is made even denser to withstand the concentrated loads. The mat foundation comprises 4 layers of rubber. Chair rubbers placed every 2 meters keep these layers at the correct height. In addition to the bottom and top grids, 2 horizontal reinforcement layers are added in the middle. After all rubber placement is complete, concrete is poured to finish the mat foundation. The mega columns built on top of this foundation play a key role in safely supporting the roof truss loads, horizontal forces, and complex mechanical loads from the retractable roof. The mega columns rise to a height of 31 meters and are not poured in one go. To control hydration heat, manage concrete pressure, and ensure stability, the columns are cast in stages. Typically, 3-meter sections are poured at a time with 24 to 48 hours of curing before the next section is placed. Mega columns have a rectangle cross-section with 57 mm vertical rubbers placed at 100 mm intervals. Unlike typical circular columns, rectangular columns have additional vertical rubbers densely arranged at the corner to reinforce critical strength points. Horizontally tied bars and stirrups are installed to resist shear forces, prevent main rubber buckling, and enhance dynamic performance. These ties and stirrups are 90 mm in diameter and also spaced at 100 mm intervals, especially denser at the corners. In rectangular cross-sections, stress tends to concentrate at the corners, so additional reinforcement is placed in these areas to enhance structural performance. After rubber placement, the formwork is installed. The formwork is assembled using prefabricated modular sections, which are positioned around the reinforcements. Once concrete is poured and reaches approximately 70 to 80% of the design strength, workers enter the column interior to dismantle the formwork by sliding it apart. The panels are then lifted out using a tower crane. After the inner formwork is removed, the remaining concrete is poured into the interior of the column. Mega columns are cast in 3-meter vertical segments, and once one segment at the bottom is completed, the next segment above is constructed using the same method. The Mercedes-Benz Stadium is supported by 19 mega columns and 8 large mat foundations. These structural elements play a critical role in effectively distributing the enormous loads generated by the long-span roof and presence of tens of thousands of spectators. In addition to the mega columns, standard reinforced concrete columns are also installed on top of the mat foundation. While the mega columns handle the majority of the primary structural loads, these standard columns support the upper floors and slabs, distributing secondary loads throughout the structure. Together, they work in coordination to ensure that both global and localized forces are safely transferred to the foundation system. Standard columns carry smaller loads compared to the mega columns and therefore use the more economical and faster auger cast pile method. This method involves withdrawing the drill while simultaneously injecting concrete, followed by inserting the rubber cages. The standard columns use rubber cages with a diameter of 60 inches and a depth of 25 meters to reinforce the soil. Each standard column typically has a pile cap supported by 4 auger cast piles. Plain cement concrete is then poured, cover blocks are placed, and bottom rubbers are arranged in a grid pattern. Next, 850mm high chair rubbers are installed to support the top rubbers, which are placed together with the column rubbers. The column rubbers are spliced using the lapping lengths and a 1:6 slope requirement method, allowing for gradual load transfer and reducing the risk of cracking and failure. To restrain the vertical rubbers, tie bars are used. Their ends must be bent to a 135-degree hook, and they should be ranged in alternating directions to ensure uniform confinements and improve the structure members' ductility and load resistance. Ultimately, all key structural components from mat foundations and mega columns to pile caps and standard columns work together to safely carry the stadium's massive and dynamic roof loads to the ground, ensuring stability and long-term performance. After the mega columns mat foundation and the reinforced concrete columns are completed, slabs of the stadiums are constructed above them. These slabs average 305mm in thickness and carried a dead load of approximately 7.2 kilonewtons per square meter. To safely support this weight during curing, a temporary shoring system was installed first, consisting of galvanized steel pipes which are 48.6mm in diameter and 3.2mm thick, are spaced every 1.2 meters. Steel pipes used in the temporary shoring system often include height adjusting mechanisms. These feature thread screws or collars that enable precise height control, even by a few millimeters. Such adjustability ensures a level formwork surface and helps maintain consistent slab thickness across the entire pour. For wider spans and heavier load zones, trusses and H-beams were added to distribute weights and support the formwork above. On top of the shoring system, aluminum stringers were placed as the primary horizontal supports. These extruded stringers provided a rigid and level basis for installing plywood form panels, which were grooved to ensure good bonding with the concrete. Inside the formwork, dual-layer reinforcement was installed with top and bottom steel mats configured in a two-way grid pattern. This two-way slab design allowed loads to be distributed across both sections, enhancing flexural resistance and reducing deflection. In high stress zones like column junctions or cantilever edges, Rubber spacing was tightened and bar sizes increased to improve structural performance. Once the reinforcement was complete, concrete was poured, compacted using vibrators, and cured using wet coverings or curing agents. When the concrete reaches 75% of its design strength, crews began removing former panels and aluminum stringers. However, vertical shoring system remained temporarily in place to allow gradual load transfer to permanent structures. Most components were modular and reusable, improving efficiency and sustainability on site. Through this meticulous process, the slab is completed, after which racker beams and precast units are sequentially installed to form overall framework of the spectator's stance. In this stadium, the racker beam is more than just a structural component. It plays a critical role in safely supporting tens of thousands of spectators and distributing the loads from the roof. As such, its construction is considered a highly precise and essential phase of the project. The racker beam was constructed using cast-in-place concrete with EFCO's plate girder modular formwork system. This system, utilizing quick bolts, is designed for fast and safe assembly of modules. The assembled formwork was precisely lifted into place using a lever tower crane. Rubber placements within the racker beam plays a critical role in maintaining the structural integrity of the system. The most important rubber is the D20 diagonal beam bars, placed at 300 mm intervals along the beam slope, resisting both tensile and compressive forces. Splicing ensures both constructability and stability. Supporting this, D16 U-shaped longitudinal reinforcement is arranged at 200 mm intervals along the main bars to hold them in place and distribute localized stress. D16 transverse stirrups, spaced at 250 mm intervals, resist shear forces and prevent structural deformance. Additionally, D10 submental bars are placed at 200 mm intervals at the top and bottom to control cracking and enhance tensile resistance. The racker beam is precisely connected to the standard column. This connection is achieved using rubber continuity and Dora rubber techniques with integrated concrete pouring to enhance bonding strengths and effectively transfer loads. The grandstands consist of precast seats manufactured off-site. These are lifted by crane and installed between racker beams, secured using grout pockets to ensure structural stability and precision. The completed racker beams and grandstands make Mercedes-Benz Stadium a safe and spectator-friendly venue. This stadium, a product of innovative design and meticulous construction, is Atlanta's pride. The components of the megatrusses were prefabricated off-site at 15 different manufacturing facilities. The total weight of all the truss members amounted to approximately 27,000 tons. The largest individual component measured about 67 meters in length and weighed up to approximately 800 tons. Due to the immense size and weight of the component, it was not feasible to transport them to the site as complete units. Instead, they were fabricated as segments, each approximately 30 meters in length. These prefabricated segments were transported to the construction site using oversized multiple axial modular trailers. Transportation was primarily conducted at nights, and more than 4,000 truck deliveries were carried out in total. During the construction of the megatrusses at the Mercedes-Benz Stadium, various types of cranes were utilized to safely lift and install the massive steel components at great heights. In particular, the Manitowoc 31,000, one of the largest cranes in the world, with a maximum lifting capacity of approximately 2,535 tons, served as the primary crane, supported by several auxiliary cranes throughout the erection process. This crane was specifically designed to lift massive truss segments, each weighing several hundred tons, with high precision within the confined space of the construction sites. It was installed and fully prepared in advance, prior to the start of the truss erection process. Once the crane installation was completed, the full-scale erection of the mega trusses began. Since the truss structures could not maintain structural stability on their own during the early stages of assembly, temporary support systems was essential. To resist this, 4 specially fabricated mega shore towers, each approximately 60 meters tall, were installed in advance. After the installation of the temporary support towers, primary trusses were first erected in a symmetrical sequence to establish initial structural stability. The installed primary trusses were subsequently connected by secondary trusses in a sequential manner. The secondary trusses were also lifted by cranes and precisely secured between the main trusses. As a result, the overall truss system formed a closed octagonal frame, completed the geometric integrity of the structure. The connections between trusses were executed with high precision using a combination of prefabricated high-strength bolted joints and on-site welding. In total, more than 850,000 high-strength bolts were used throughout the structure. For certain large connection points, field welding was employed to fully integrate the steel components, ensuring both connection rigidity and overall structural safety. Each of these trusses is directly connected at its ends to the top of the mega columns. Specifically, one end of the trusses is designed with a pin support, while the other utilizes a roller support. This configuration allows for horizontal movement caused by temperature changes while ensuring that vertical loads are safely and effectively transferred to the supporting structure. After the trusses were fully connected, a hydraulic jack system installed at the top of the mega shore towers was used to precisely control the load transfer. Through a gradual and carefully monitored process, the load's initial support by temporary towers was progressively shifted onto the permanent mega truss system. Once it was confirmed that the load transfer had been fully completed, the temporary support towers were gradually lowered and dismantled. Through this process, the mega trusses became structurally self-supporting, no longer relying on temporary structures, and the system was finalized in a stable and independent state. To enhance the precision of this complex structure construction, Tekla-based BIM technology was effectively utilized. The project was successfully completed through close collaboration among several specialized firms including Warner P. Moore, Can-Am, and Maxim Crane.